In this video I want to talk about how we can use the vector product to calculate areas of certain shapes. So I want you to think about two vectors, OA and OB, which we could use as we often do. The notation may be lowercase a and lowercase b for those position vectors. And we're going to position them such that they're tail to tail and there's an angle of theta between them. Now we could consider those two vectors as spanning an area. It could either be an area which is a triangle, that would be by joining A and B, or we could consider it as spanning a parallelogram. So if we sort of put the vector A up here as well and the vector B along here as well, then we could say that the vectors A and B span the area which is that parallelogram. So let's maybe give this another, we'll call that point up there C. So how could we find the area of OACB? Well, the area of OACB would be what, base, so by there I don't mean the vector B, I just mean the base of the parallelogram times its perpendicular height. So let's draw in the perpendicular height just here. So base times perpendicular height. Now consider that sine theta is going to be equal to what? Opposite in this right angle triangle here. So the opposite side of that, which is h, over the hypotenuse, which is the magnitude of b, isn't it? So it's going to be h over magnitude of b, and so therefore we could say that h is equal to magnitude of b sine theta. Alright, so here the base of the parallelogram is the magnitude of a, so that's, and the height, this height as we've just said is magnitude of b times sine theta, magnitude of b times sine theta, but that expression there, magnitude of a times magnitude of b times sine theta, is in fact just the magnitude of the cross product, isn't it? Because if we stuck the unit vector n on the end, we would have the cross product, and so without that unit vector what we have is just the magnitude of the cross product. So in other words, we can find the area of a parallelogram that's spanned by a vector A and a vector B simply by calculating the magnitude of the cross product. Now remember, the cross product is a vector, but the magnitude of the cross product is going to be a scalar, isn't it? So we can work that out, and that's easy in component form. Now, when you think about the fact that these vectors could be in three-dimensional space, they're three-dimensional vectors, that in fact is a really simple way to do something that could be very complex. We can extend that just a little bit further and say, well, if we wanted the area of triangle OAB, well, it's simply half the area of the parallelogram, isn't it? So it follows that area of triangle OAB is going to be a half of the magnitude of the cross product, simply because it's half of the area of the parallelogram.